just two things in number. The first one of which is to thank Kevin. You may not know this, but Kevin has actually chaired our guest lecture series now for a year and a half, and I think that he's done a marvelous job of bringing a remarkable group of people to the college. So I'd like for you all to join me in thanking Kevin for a remarkable job. Secondly, I want to talk a little bit about next year. You may be, I hope you're aware by now, if you're not, that after your student organization leaders, that next year is the 40th anniversary of the college. The college was signed into law in March of 1965, and because of a variety of reasons, we've decided to dedicate the entirety of next year to our alumni. Partly because we've got remarkable alumni who are doing remarkable work out there in practice, most of whom come back here and when they talk about how they're able to do it, talk about the education they got here. And they talk about it in terms which are pretty remarkable. So we're delighted to have them come back to, first of all, tell you how they got to do what they currently do, and secondly, for you to be able to get a chance to talk to them about how you get between here and doing some of that work. I've had conversations now with Craig Hartman, and he'll be back, and Tom Kerwin from SOM, San Francisco and Chicago, respectively. Eric Ernstberger will be talking in that series. Tom Doolittle is coming back from HMTB in Boston. We've got 5 or 6 people already lined up. I assume we'll have a full lecture series of people who are doing pretty remarkable work out there. And that will be our lecture series. They'll also be exhibiting their stuff during the year. So stay tuned to a year dedicated to looking specifically at the work of our alumni. And with that, I'm going to turn this over to Kevin to introduce today's final speaker for our fall semester of the guest lecture series.
Thank you, Joe. Okay, it's my distinct pleasure. First of all, I'd like to say it's great to see that you all turned out. I know this is the end of the semester push, and I know a lot of you are probably very sleepy right now. But it's great that you all turned out at such numbers. And in fact, throughout the entire semester, you guys filled the auditorium, and that is to your credit and a couple of others. So thank you all for your being here. It's my distinct pleasure to welcome Joe Burns to Ball State. Joe is the managing principal at Thornton-Tomasetti, and he's an engineer as well as an architect. Mr. Burns joined the Thornton-Tomasetti group in 1995 with over 16 years of experience designing new structures and renovating existing buildings. Mr. Burns graduated from another university north of here called Notre Dame in 1978, and went on then to MIT and graduated from there in 1981. Mr. Burns is well known for his innovative structural design work, of which you'll see a number of projects today, both big and small. These projects have a significant magnitude as well as a degree of complexity in the realization. And Joe has really made a name for himself as becoming the go-to person to resolve complex structures and working with projects that are innovative, that require innovative structural design work. He specializes, in fact, in designing complex structural systems, including earthquake engineering and dynamic analysis. He served as adjunct professors at University of Illinois, as well as IIT. He's also an avid member of many associations, in addition to being a fellow at the AIA. Some of the projects that you'll notice, there's one on the poster, is the Soldier Field Adaptive Reuse, which was it was named the best large structural project in the Structural Engineers Association of Illinois' Excellence in Engineering Awards competition. As well, it's been honored with a Merit Award in the American Institute of Steel Construction Ideas Award, a Merit Award from Chicago Building Congress, a Grand Award in the Building Team Project Awards by Building Design and Construction Magazine. Other projects that you'll know, he's worked on so many projects, but the ones that I just want to point out to you are the Indianapolis International Airport Midfield Terminal project. He's working with that, as well as another Indianapolis project that Joe's worked on is the White River Gardens Conservatory and Botanical Complex, for those of you that like to go to the Indianapolis Zoo. that's just a couple of a huge list of projects that you're going to see right now. And we're very, very grateful to have Joe Burns with us to talk to us today. Let's welcome to Ball State, Joe Burns.
Let's see, is this on? Everyone here? Okay, good. Thank you, Kevin. And well, I probably have too much to squeeze in today, but when I got talking with Kevin about what to talk about, it occurred to me that I get asked often by architects when I'm consulting whether this project is too small for us or for me, and I usually answer is no, it's not. We like small projects, and in fact, the whole point of putting these two things together is to show the interaction between the things we learn on big projects that come back to help us on small ones, and vice versa. I'm going to work from big to small, and in fact, there's three parts to this talk: tall, wide, and small. And the wide, I'm going to branch out into another area of interest of mine because it relates to a specific area of our use of 3D modeling technique and how that interfaces with the industry, the construction industry, and one that I think which should be interesting to you as you students work out into the industry. You'll find that there are a lot of revolutions happening out there. So I'll start with tall, and of course, tall's been around a long time. We Thornton-Tomasetti had the good fortune to work with Caesar Pelli on the Petronas Towers, another twin towers. But there have been a lot of others that certainly coming from Chicago, that was probably one of the reasons why I went to Chicago many years ago, was to learn tall building design. I worked at SOM for a number of years. And of course, these are all examples of the history of tall buildings. And it's not over, of course, as you probably read in the news, some big ones out over in the Middle East that are underway. All the way from Gothic through Gaudi, the Washington Monument, and the Eiffel Tower. Chicago holds a special place, though. It is, certainly for Chicagoans, and I think many others see it as the birthplace of tall building design. If one takes as a definition of a tall building as a self-supporting frame, in this case a rigid frame, with a separate facade system. In this case, at the home insurance building, the brick was clipped onto the frame, and many found that as a definition of tall buildings, opposed to load-bearing structures. This is another example of a William LeBaron Jenney building, the Fair building, which shows that interaction between cladding and structural frame. Well, there are a lot of reasons why I think Chicago was the center. There was a development of fireproofing for grain elevators, which were more of an industrial product, but turned out to be very useful in the fireproofing of tall buildings as well. Elevators were invented. It's not clear exactly where they were invented. They were used in New York and other places, but it was a very critical element that came together more than a century ago that made them viable. Well, in terms of focusing on Chicago again, the Monadnock building, which is not viewed as in the same class as the home insurance building because it's a load-bearing building. It doesn't have a self-supporting frame. Nonetheless, it's part of our rich history in Chicago. Of course, cladding, these are examples not from Chicago, but the different kinds of cladding from curtain walls to glass cladding. The Civic Center building probably is, interestingly, one of the more heavier buildings. There's a sort of drive for efficiency over a number of years, but this interfaced cladding technology along with the structural frame, which is a huge rigid frame. And again, going back to the sort of origins of Chicago tall building development, I had the good fortune to work with Myron Goldsmith, who was a partner at SOM He's passed away now, but he evolved a series of buildings with his thesis at IIT with Mies van der Rohe, which explored ways of scaling tall building structures coincident with how tall they are, and also using the structural concept as part of the architecture. And he also evolved a series of systems that were scaled to the height of the building. And the notion was that there was a certain scale to a building structural type, not something that could be just enlarged without end. There were a number of projects that he worked on with students when he was teaching at IIT, and many of these worked their way into the offices of SOM with both Myron Goldsmith and people like Balthazar Korab, who were the structural engineering partner at Skidmore and taught at IIT as well. These were concrete tubes, which Balthazar Korab sort of invented and utilized in a variety of ways at SOM. That sort of culminated in the bundled tube concept that was fundamentally the structural system for the Sears Tower, the tallest building in the world until just a few years ago, when it was surpassed by the Petronas Towers. But now, of course, there's more in the wings. The Taipei 101 is exceeded that, and then there's, as I mentioned, really tall ones coming in the Middle East. There were other systems, other buildings that used this structural expression of the perimeter tube. The Antares Center, which was a concrete tube versus the steel tube of the Hancock building. Recently, we worked on a project in Chicago, scaled much smaller than the Hancock building, but utilized a structural frame for a project called Erie on the Park with Lucien Lagrange. It's an all-steel apartment building, not unlike the Hancock building, but we utilized a technique of 3D modeling of the steel frame to help procure the steel frame and have it fit together. And I'll touch on this more in the second part, but I wanted to sort of mention it briefly here. But it did utilize sort of a super frame for that building. And it was part of the architecture. And there, of course, there are many examples of these type of buildings from New York to Hong Kong. The City Court building, on the other hand, and I did have the good fortune of working with Bill LeMessurier as well, who designed this building. Bill worked with an architect, Hugh Stubbins, who didn't feel it was important to express what was a very efficient building, but rather clad it with aluminum and glass cladding. You can see it at night, though, when it's lit up. One Liberty Place by Thornton-Tomasetti and Helmut Jahn shows another type of structural system that begins to show the evolution of tall buildings from the tube buildings, which were sort of dominant in the 50s, 60s, and 70s, and certainly the hallmark of SOM, to other mixed systems. This is a system of core bracing and outriggers. And systems like these are in a sense the combination of which are making the tall buildings of today. I mentioned one other super frame when I mentioned the sort of evolution from the work of Goldsmith and Kahn from 1953. This was his thesis at IIT. Which involved a series of super frames, and this was a project just actually when I was starting at SOM that maybe one of Balthazar Korab's last projects before he died, which was again a super tall building, but with a super frame concept. Concrete and steel. Most of what I've been talking about is sort of steel frame buildings, but there are a lot of concrete buildings in Chicago, particularly apartment buildings, and most notably, and from the beginning of their evolution in the 50s, the Marina City by Bertram Goldberg. But there are many others. This is the Swiss Grand Hotel, which is a triangular building, a series of residential towers by CBM, which was a predecessor firm to Thornton-Tomasetti. We merged with them in 1993. L.E. Cohen was the engineer there. It's a whole series of sort of residential buildings, and not just by us. It's a sort of very common building type in Chicago. Of course, though not as common, we see concrete office towers. This was the Xerox building, one of Helmut Jahn's first sort of breakout buildings, I think, in terms of his notoriety, and a whole series of other office towers. I wanted to spend a little bit of talking about where things changed from that notion of a perimeter structural system to what I would call an internal structural system, or some combination thereof. And Louis Kahn tells me that he did about 50 of these buildings, again, the predecessor firm to Thornton-Tomasetti, a series of hyperbolic cooling towers which utilize a sort of concrete technologies called jump forms to construct them. And in fact, either with jump forms or slip forms, the whole notion evolved in the 70s and 80s, really opposite of the SOM notion, which was, why not build a concrete core around the elevators and stairs and let that be the structure, and let the structural frame around it be just very simple. And it allows for much wider open column grids, in fact very efficient because you're using concrete, which is a more cost-effective material in the middle, and of course where it can be most dense. So this is a whole series of buildings that were done in Chicago using this technology, which isn't so evident because it's not expressed on the outside of the building. In fact, anything you want can be expressed on the outside of the building, as evidenced by Ricardo Bofill on the left, or Kevin Roche and John DeCalou on the right. This is Kenzo Tanguy on the left and Caesar Pelli on the right. So again, these are very similar structural systems, but different dresses. This is Helmut Jahn at Oak Brook, and then Philip Johnson at 190 South LaSalle. Recently, we're still building them in Chicago. These are 3 recent projects I've been involved with. UBS Tower with Lohan Caprilli Getch on Wacker Drive in Chicago, 191 North Wacker with Cohn Pedersen Fox, and then ABN AMRO with DeStefano and Partners. All of them fundamentally concrete core buildings with very simple steel frames. And maybe a building that wasn't constructed, though Thornton-Tomasetti went a long way with it in terms of getting building permits. This was a 2,000-foot tall tower, which would have been the tallest building in the world had it been built in 1990. Very, very slender. And this was, in my view, one of the sort of turning points, away from massive sort of steel structures like the Sears Tower towards concrete structures for the tallest buildings in the world. This building, after a number of wind tunnel tests, it was decided the only way to build it really was in concrete because of the mass damping, the efficiency of material, and at least in Chicago and now in many parts of the world, high-strength concrete that's available. So here it is in the wind tunnel tests. As I said, a lot of work was done on this. This is the other thing. I think maybe one of the themes I wanted to leave with you today is the things you learn on one thing, you don't know when it's going to come back to help you later. As I mentioned, either on small projects or big projects. This was the plan, which was also very innovative at the time, notion of a concrete core and then massive outrigger columns that would serve as the only both gravity and lateral systems for the tower. And again, these walls, massive walls, which were done in reinforced concrete. So that project died, and then in the middle 90s, there was a competition for the Petronas Towers for Petronas. It wasn't, the winner, as it happened, was a Twin Towers by Caesar Pelli. And it didn't start out as the tallest buildings in the world, but it did start out with very similar structural systems as the Miglin-Beitler Tower, basically reinforced concrete, outriggers, a core wall, and structural steel framing. There were a number of complexities with the project. There were foundation issues that had to be solved that could have resulted in tilting towers like the Pisa Tower. That was solved with sort of moving the towers a little bit. This is sort of one of the things that happens in big buildings is the number of intricate problems sort of multiply. Many of them small problems in and of themselves, but added together, big problems. In this case, a very complex foundation system. Wind tunnel testing, as we do on most of our tall buildings, both with and without the future buildings. And a relatively complex superstructure system, which consisted of erecting this concrete core wall system I mentioned earlier, a series of perimeter concrete columns and girders, and then filling it in with structural steel framing, which is this mix of composite and steel and concrete, and then the steel balconies. And then as in the building sort of advances on upward. And outriggers which allow for the increase of the width of the building through these coupling girders and trusses. So here's some pictures of Petronas Towers under construction. There are actually two different contractors, a Korean and a Japanese contractor, and they raced each other, which was a good thing for the owner of the building. There were a number of other smaller problems. These sloped columns, as the building gets smaller, how do you slope it? You slope them gradually rather than big transfer girders. And of course the sky bridge was very complex as well. It was used as an exiting mechanism, but it was also a very important symbol of uniting these two towers visually. And again, in a sense, a small problem, but part of the bigger problem of a bridge system. They even demanded tuned mass dampers to avoid wind vibration in certain wind speeds. And that's a sort of theme that comes back in many of our projects is vibrations, particularly due to wind. And in the case of Soldier Field, due to crowd vibrations, are issues we deal with as structural engineers. A project that, there's a lot of projects, of course, don't get built, but again, as I said earlier, you learn from them. This was a project in late 90s called Project 2000. The idea was to have it built by 2000. It would be 2,000 feet, but alas, that didn't get built either. This was clad by Ricardo Bofill on the right. Maybe not the right image, but there it is. And here we actually got as far as wind tunnel tests. This is actually in the test tunnel along with SOM's 7 South Dearborn. This was actually competing for that same owner. As it turns out, they picked SOM, but of course neither of us won. But none of those projects were getting built. This is an odd test in the most unlikely event that both of these towers would get built. I guess we had that other tower in there. We were involved in the consulting on the current tallest buildings in the world, Taipei 101. That too has a tuned mass damper, very, very heavy. It's an all structural steel building. It probably, for everything I said earlier about the change, you could ask the question, why is the tallest building in the world all structural steel? Well, it was funded in part by the Taiwanese steel industry. And so they didn't really care how heavy it was or how much it cost. It had to be all steel. But I think economics would have suggested a different system. This is the structural system I mentioned earlier, a whole mix of, same idea, core brace system with outriggers, but you can use these things interchangeably. Very complex tuned mass damper. It's actually a pendulum hung from the top of the tower, and it swings. There's actually a bar around it so you can watch it move if it's windy outside. And I finished tall. We seem to, well, see how we're doing here on time. I'm going to move on, but I just want to mention a concept of space elevators from NASA. NASA is actually working on this now because materials exist now to make this possible. They thought of this in the 60s, but didn't think materials were possible to do this. But now with carbon fiber, the whole notion is of a space elevator to build a platform far out in space in geosynchronous orbit and connect it up like a pendulum with carbon fiber and send elevators up and down. So this stuff, this is as tall as you could go. But let's move on to another thing. I'm going to move fast here. We're going to go to wide, but I might, and this part two, as I say, interlaces this concept of what's going on in the AEC industry. The architecture, engineering, and construction industry is in transformation, primarily due to three-dimensional modeling. I suspect many of you now are experiencing that in school from Form Z to other programs, but it's actually affecting business in a sort of unusual way. And I'm going to talk about that and some big buildings, big wide buildings, particularly Soldier Field and the airport that were mentioned earlier. But this transformation is coming from two ways, top down and down, and from bottom up. And from the top down perspective, construction owners, this is Construction Users Roundtable, that are saying that there's a number of problems with project coordination these days. Things are moving very quickly, and that, in fact, we have to think different about utilizing new technology. And one is that with the advent of 3D modeling, that one needs to work more earlier. And this is the sort of a sketch from a committee that I'm on, the AE Productivity Committee. But the whole notion is that the owners need to take, in their view, leadership in integrating the building process, that three-dimensional information needs to be openly shared, not sort of held internally. Because basically what's going on now is everybody's got their own models, but what's being shared are two-dimensional information. It's a little like medieval scribes, where you're sending information over and having people recopy the three-dimensional information. The question is how can we increase that productivity of the construction industry? The auto and aerospace industries have already done this, and they've achieved tremendous increases in productivity. So again, this is a notion that the traditional design process, which is in black, suggests that we start out with concept design and schematic design, design development, and we have our peak of work, peak efforts during construction documents, where we produce the drawings that we're going to use to construct buildings. In fact, the way things work, the ability to affect the impact of cost and functional changes decrease rapidly during the design process. And of course, the cost of changes to the design increase. So the idea is that, in fact, we need to move up earlier into the process our efforts of three-dimensional modeling. So in any event, the Productivity Committee envisages much more interactive collaborative teams. At the same time, there's a number of industries that comprise the construction industry that are working up the other way. And probably the most notable among them are the steel industry. The steel industry is a global industry now. Steel is shipped all over the world. The steel was detailed for Soldier Field in Perth, Australia, and in England. It is truly a global industry. And of course, it doesn't just serve the construction industry, it serves many, many industries. The thing that in terms of speaking of productivity, all industry has increased rapidly from the 60s through the last few decades. And that's the red mark. Having said that, the green mark represents the construction industry, which has actually lost productivity over the years. And one wonders, how can that be? And a lot of it is, of course, this is a very labor-intensive industry where a lot of things go on site. Interestingly, the steel industry has similar loss of productivity when it comes to steel erection, which is the on-site portion. But the fabrication side, which is really more of a manufacturing side, has experienced exactly the same productivity increases. And they've done that through products like this. This is, again, this tall building area in the park. This uses a program from Finland called X-Steel, which models every bit of steel, every connection, every bolt, and it integrates both the design side in through the supply chain of fabricating steel. is an example of the top of Erie on the Park. We've learned this through a consulting engineer in London, Whitby Bird, who utilized this same technique of using the software on the design side and saw increased savings over time as he used it, meaning the steel, it was really creating a commodity for steel once one gets this complex stuff out of the way if steel is being fabricated by machines. And conversely, fewer and fewer RFIs or requests for information during the shop drawing phase. And the thing that's been driving this is a integration standard that was agreed by it was invented by the Europeans but adopted by the North Americans as the North American standard, and now it's become a global standard for computer integrated manufacture of steelwork. And this standard, software companies are now writing to. And it's really important that it's an open standard, and it's one that, as I say, is showing up more and more in software we use in the steel industry. And the whole idea is to create a standard by which we can pass information along the chain from drawings and analysis and design through fabrication, costing, and planning to make, again, that particular product more efficient and thereby the whole industry. Well, this integration continues. This is an example of 3D modeling of Soldier Field. I should say that in terms of structural analysis and dynamic analysis, I should say that we, at the time when we worked on this in 2000 or so, 2001, that integration didn't exist, so we did have to copy this information over. This same software today would be integrated with all of the X-Steel models. So that's how much things have changed just in a few years. This is one of the big cantilevers for the scoreboards at Soldier Field, based on that model I just showed you. And this is actually how we check shop drawings. The three-dimensional information was shipped back and forth from steel fabricators, the steel detailers in Perth and our offices in Chicago. And the reason for this is most steel fabricators that are still in business have invested heavily, millions of dollars in equipment like this that cut and punch steel. And it's very important that these machines are driven by computer code, and this computer code is downloaded from software programs like X-Steel. The steel industry has also adopted standards for things like, just simple things like barcodes that, again, have increased productivity. And as all of you know, the things that the people like Walmart were way in front of us on that. But again, these are the kind of things that are going to make costs of building your building designs more cost effective. Next, there aren't too many of these industries that have taken this, but just recently, and it's an important change, is the precast industry, precast concrete. These are a couple slides I picked up from, I was at a talk recently at Iowa State, and I'd heard about this, but this precast concrete software consortium have hired the same software company that did X-Steel, Tekla out of Finland, to create a very similar modeler for the precast industry, one that would integrate the supply chain. They hired Chuck Eastman from Georgia Tech, who's one of the experts on 3D modeling and the interaction with engineers. And so they were chosen in 2002, and we actually have the beta version of it, but the whole notion is to support automated engineering and detailing, literally detail all the rebar inside of a precast element, hopefully reduce and eliminate errors, improve quality, support their plant automation. But this is the most fascinating thing, is right now when they get a project in a precast yard, it takes them 6 to 8 weeks of engineering time before they can be out in the yard. Now, again, this is a goal that they may not achieve, but they think they can get it down to 1 week. And that will translate directly into the cost of precast products and the speed at which one can move. My hope, of course, is we get more time in design then, but that's not usually what happens. The cladding industry is not as well organized, the enclosure industry. This is, of course, the thing that's driven a lot of this, and I haven't mentioned Frank Gehry yet, but we all owe him a lot. His group that produces his buildings has been one of the leaders of using 3D models to move the industry forward. One could say that without that technology, he couldn't be building as much as he is building, but nonetheless, I think a lot of people, particularly cladding contractors, have picked this up. Premise Lisa is one of them. They're out of Italy. They have adopted 3D modeling throughout their production methods, both in terms of design but also fabricating, to take advantage of the information they can get from people like Frank Gehry. The other area that is really got a long way to go, but it's very critical, particularly from a sustainability standpoint, is the MEP, mechanical, electrical, plumbing industry. This is an example of the Disney Concert Hall, where everything is integrated, all the ducts and pipes and everything with the structure and the cladding. But that's the exception. In fact, there is a massive MEP global community that works on petrochemical projects and others that are totally 3D, but they don't seem to work on buildings. So there's a long way to go there, but it's very critical, I think, that if all this is going to work. There is a consultant in Finland, Olof Granlund, why is it that all these people are in Finland? It's because of Nokia. It's such a small country and they can't get people to move there that they realize that they have to compete with Nokia in Finland in order to get smart architects and engineers to work for the construction industry rather than go to work for cell phone makers. So there's a reason why all this is going on in Finland. But anyway, this is a company, MEP company, that only works in 3D. They have a total three-dimensional workflow. The job comes in the office, it's instantly in 3D. So that's, you won't find anybody like that in the States that I'm aware of. So here's some examples of some of their work using software that's developed in Scandinavia. And of course, this all comes out of the 3D model into 2D drawings. All this is about this notion of a building information model. Maybe some other people have talked about this, but it's a notion that's moving rapidly forward in the building industry. The GSA is talking about piloting projects where the whole team will work in 3D by 2006, at least in pilot projects. And you would produce a three-dimensional computer model as part of your deliverables. The whole idea is that this model is accessible to everybody on the construction team, not just the design side, but the subcontractors, surveyors, fabricators. With that in mind, and it's not clear, we're working on, as I mentioned, on the Indianapolis airport. This is a structural model of the roof in X steel, which we worked on in schematic design. There's some examples, again, of using 3D in the structural side early on. This is some of the details, again, where you can actually see how things come together. We haven't really got into the connection design yet, but you can get a sense of how things are fitting together. I threw in a couple of images of the airport for those that might be interested. This is, again, HOK is the design architect. There's a whole consortium of Indianapolis architects and engineers that are working with that. We were the design engineers, and in fact, there's a Indianapolis structural engineer that's the engineer of record. Exactly how it's going to be procured and how 3D will be part of it, I don't think has been decided, because all of these things have legal implications. It depends upon the contract type. Of course, there are lots of advantages to utilizing this technique, but it's still working its way through the system. This is an example of the airport roof. You can see the circular atrium area on the other side of security, which I have an image of. This is the arrivals, or rather departures area, and this is that open area on the other side of airport security. And Thornton-Tomasetti is continuing to move the notion for, at least on the structural side of 3D, we're working on, we have now a small group and growing group in Kansas City that's doing three-dimensional modeling for steel detailing. We think that in order to achieve real benefits, we have to bring that kind of service into our practice. Again, an area that traditionally hasn't been done by engineers. This is a concrete building. We have our new Tekla modeler does concrete as well as steel. As I mentioned, eventually we'll have the version that does precast. And finally, Soldier Field. And these are some sort of our use of, this will have some images of Soldier Field as well, but our use of 3D modeling, I think, allowed us to achieve this very critical goal of finishing in 20 months. The Chicago Bears did not want to be out of Soldier Field for more than one season, which meant 20 months. There were a number of roadblocks, including the 9/11 delayed the season one week, and then also inexplicably the Bears were in the playoffs that year, and so we actually were delayed more like a month. So we got going, and just to back up a little bit and talk a little bit about Soldier Field. This is the lakefront in Chicago. This is actually a picture from Charles and Ray Ames's book Powers of 10, which interestingly was focused on Soldier Field. I picked the picture because you can actually get a sense of the way it looked when the Soldier Field was encircled by Lakeshore Drive. In fact, in the end, the goal was to create a stadium in a park. Of the $600 million or so that was spent, $100 million was spent outside of Soldier Field on the infrastructure. And of course, that all had to be done in time too for the opening day. But what was very interesting about Soldier Field, there are no stadiums like it. It's very asymmetrical. All of the clubs and skyboxes are on one side of the stadium, and the other side is a very open-air grandstand stadium, which was done to squeeze this into Soldier Field, the existing walls of Soldier Field, which I'll show you in a bit. But this was our use of the X-Steel modeling on the scoreboards. These are examples of the grandstand modeling and the structural steel. And this is the sort of detail that you can get to in the shop drawing review, where everything, in fact, does fit together, and that's, in fact, the beauty of it when you're out in the field. Things do fit together because these products have been cut and punched with machines, not unlike a three-dimensional laser printer. This is an example of the skyboxes. And now I'm talking a little bit about the other uses of this, now that we had a three-dimensional frame in X-Steel. The good news is they hired Promotional, the same fabricator I mentioned earlier that had done a lot of Frank Gehry's building. This of course was simple compared to Frank Gehry's buildings. So they were delighted to take our X-Steel model and clad it and clothe it with glass and steel. And it was all panelized. It came in these pallets that you see on the left, or the right rather. We detailed a lot of cladding in X-Steel in the case of the stainless steel cladding on the underside of the bowl. And precast, well, that's the one area where we could have used this new product that's just being invented. We had a lot of conflicts between the precast and steel. The precast was detailed in two-dimensional world rather than a three-dimensional world, and we're looking forward to a future where these two materials are married together. The other big problem we had was MEP, which I mentioned earlier, mechanical, electrical, plumbing. In this particular case, it looks like there's lots of room, but in fact, there were lots of other places where the mechanical just didn't fit, in part because the mechanical contractor didn't get on board until after we had already finished checking all the shop drawings on steel. So it was inevitable that we were going to have problems there. So I'm looking forward to a future, again, where we see more interaction between structure and mechanical in 3 dimensions. These are some views of the concourse on the west side, where you can actually walk around the colonnades again. This is a view inside the stadium from the big grandstand. By the way, there's little doors up along the back wall. Those are access hatches for tune mass dampers that we designed and installed inside the tip of the cantilever to reduce vibration. So it goes back to those small problems within big problems issue. And this is a really interesting view in the north grandstands where you're looking inside the stadium and sort of outside at the lake at the same time. Very complex project. You still see downtown skyline from the north end. And this is a view from the lake. Well, I've still got 10 minutes, and Julie tells me I can use up 6 minutes that she didn't use when she was talking, so I get 16 minutes. I'm going to go to small now, and I have some images. A whole range. I have the good fortune in Chicago to a lot of people that used to work at Skidmore don't work there now, and they're doing interesting things. People like Dan Wheeler. I do a lot of work with Dan. This is a series of houses, and now he's doing bigger projects where, again, there are other kinds of issues, but the same detailing issues that arrive, and very often trying to find cost-effective solutions for these houses. Not all the time, but many times. This is a case of very simple laminated timber, bent, rigid frame that was utilized extruded in a vacation home in Michigan. This was a project we just won with Jeannie Gang. This was for an environmental center, the Ford Environmental Center, which utilized a whole series of recycled reinforcement bars woven together like a nest. We also drove H-piles into the ground at various angles to support this concrete roof. Interestingly, this idea came out of our use of H-piles on Soldier Field, where we were driving them in on angles to resist lateral load for wind due to the poor soil conditions out there. But this was a case where we're trying to reuse. This needed to be a platinum LEED building, and so we're reusing structural steel from recycled industrial buildings in the area to sort of take these objects and drive them into the ground and reuse them. This is a very simple bridge on a private farm that I worked on with John Vinci. Very simple structural steel, Corten steel, rigid frame that uses Vierendeel action. And then maybe a little more elaborate. I do a lot of work with David Hovey, who is an architect, teaches at IIT, but has his own development business. He is an architect developer. He develops massive projects, obviously very successful. This house overlooks Lake Michigan up on the North Shore. But I've been working on a whole series of little deck additions where he is much more interested in how thin it is rather than concerns too much about flexibility. He's okay with bounce in terms of vibration. This is a project with Doug Garofalo for an exhibit in downtown Chicago, Earth from Above, where we engineered the various platforms. And I've done a lot of work with Doug. Julie Flores has done a lot of work with Doug over the years. These are little Exelon pavilions near Millennium Park that we engineered with Tom Beebe. In fact, we did the whole theater complex, very modern use of precast and other elements, very cost-effective theater, music and dance that Tom Beebe did in the middle of Millennium Park. This is a little stairway. I enjoy doing stairways. I've been doing them for quite a few years now, and every one of them is different, but their stairways are a very complex structure which has to achieve, particularly if they want to be thin, success in not bouncing too much at the same time, very clear needs for handrail and integration of handrail into the structure. We do a lot of theaters. This is the Looking Glass Theater Company, now housed in the old pumping station for the water tower up on Michigan Avenue. It's a very modern theater inside of a 19th century building. This is a stairway we designed with Dan Wheeler-Kearns for the Marwin Foundation, very simple steel structure. I did a series of sculptures, engineered them rather, with 4 different architects at the National Building Museum. Stanley Tigerman was the curator of these 4 exhibits of masonry. This was Jeannie Gang's stone curtain of a very thin marble curtain interlocked like puzzles. This was a terrazzo wave by Julie Eisenberg from LA. By the way, Jeannie's from Chicago. This is Carlos Jimenez from Houston, a brick sculpture. This is actually moves around and sort of the use of post-tension brick. And finally, a series of AAC aerated, autoclaved aerated concrete, a very lightweight block, which was sculpted by Vinka Dubadim from New York. This is a sculpture that we engineered with Doug, and Julie worked on this as well, on the steps of the MCA, Museum of Contemporary Art in Chicago. It's a whole series of lightweight structures that were anchored by these precast blocks of concrete to keep it from blowing away. And this is a whole series of elements that, again, some of it had to be engineered by going out and shaking it and seeing that it worked okay, because, well, as try as we will with sophisticated engineering technique, sometimes you just have to go out and shake it to see if it works and decide whether you need to add a few more bracing elements. And so this is it on the front steps. We worked on a series of exhibits with Doug. This is the Museum of Time at Museum of Science and Industry. I guess it's down now. I saw it. I was there recently and it wasn't there anymore. So where did it go?
I don't know, but the city never paid its bill.
Oh, that's why it's not there. Okay, that would explain it. So anyway, it's not there anymore, but we have pictures, and it's a very interesting series of a sort of ramp system and use of new materials. And this is a spiral staircase at the National Italian American Sports Hall of Fame. It's a long-winded word, but that's out near Taylor Street in Chicago, near UIC. It's a very interesting spiral stair with John Vinci. It's the handrail design. This is a structural steel frame for one of house by Doug Garofalo that we've engineered. And finally, a series of big houses in Arizona with David Hovey, where he's utilizing just structural materials as the structural system. These are, in this case, Corten steel. That's really a lot of fun working on these. This is a precast house with Dan, very low-cost house on North Avenue with Dan Wheeler using just simple precast. We actually, in the end, just designed the foundations on this and bought the precast from a precaster. I think someday they'll be oops, go backwards here. They will be modeling this in 3D and maybe doing even more fun things than this. This is a house called Tower House with Rick Phillips in Chicago. It's a very simple frame, very lightweight frame, which uses, I don't know if you can see it, but just in underneath the beyond the car is a sort of box. It's a box of masonry. We looked at in concrete and a bunch of other things, but fundamentally this is, in small part, one of those tall buildings I was telling you about earlier, the core wall buildings. The only lateral resistance system is that box of masonry. And we've attached on this very light steel frame, and it sort of is along for the ride, which allows it to be, of course, very lightweight. It doesn't have to be heavyweight, big chunks of structural steel and bending. It's just very simple framing. So I think this is one example of that. You know, how does an idea from something big get transcended down to something small? This is a picture from the back with that masonry box, which is basically a stairway and I think a potential future elevator if they needed one to get to all the levels. We've done a lot of unusual projects, special projects. In this case, this was a movie that we did with Warner Brothers, where we designed all the structural steel gimbals or elements that move an airplane around. The movie was U.S. Marshals with Tommy Lee Jones and Wesley Snipes. And they shot it, the reason why we worked on it is they shot it in Chicago, and I think we're the only engineers that said we'd do it, but we had to roll this 727 fuselage around, and you learn a lot of things from that, things that, again, come back later when you're not expecting them. This was a picture of another gimbal that moved up and down. This is White River Gardens, the botanical garden we worked on with Woollen, Molson and Partners. I actually was a partner of Evans Woollen Molson for a while. I left Skidmore for a few years and worked as an architect and an engineer with Evans for a few years in the 80s, and it was still work on a number of their projects, so it's a really good friend, good designer. I know there's some Ball State grads in that office. In any event, this is some views of the exposed structural steel inside of the botanical garden and a view from the front. And I think this is my last image. This is speaking on the small side, this is another zoo. This is the Lincoln Park Zoo in Chicago. We worked on a fabric roof over an existing building which houses now a carousel, but the idea was to make a very simple modern covering for it in lieu of the sort of 19th century carousel which is below it. And I think that's it. Thank you. Any questions?
Thank you, Joe. We have time for some questions. Just raise your hand over now.
Yes, Joe.
Joe, what you showed us is so atypical of what we think engineers do. How did you get from an engineering education to do work like this? Because it seems very unusual.
Well, I think in part because I started out in architectural education at Notre Dame. I got a Bachelor of Architecture there. I had a good fortune of spending a year in Rome there, which I guess they still have. I'm not happy with the direction they've gone down in the last few years in terms of their classical path, but because I don't, quite frankly, think that someone like myself would have been nurtured there today to go in the direction I did. Had very strong support from Ambrose Richardson, who you may know. He's passed away now, but he was the chairman of the department when I was there to pursue both engineering and architecture. I got a double master's at MIT. And I guess I've always been interested in the importance of structure in the design of buildings. I really do think they're important. I think a lot of other people do too, and that's been nice about working in a place like Chicago. I don't know that I completely answered your question, but you have to work at it actually.
Thanks so much for this extraordinary presentation. I'm thrilled to see all the wonderful exciting work. I have a really very technical and practical question. When you change the decision-making structure pattern in delivering complex buildings, for example, with the CAD-generated machine parts and so on, how do you deal with labor union issues? Or do the labor union jurisdictional boundaries cause any difficulties in delivering these extraordinary projects?
Well, I don't have an answer for you there. I wish I did. First of all, typically the issues, a lot of the things that are going on here are factory driven. For instance, steel, whether you use machines in the factory or not, and the factory is more productive, the guys out in the field don't care. In fact, things like Soldier Field, there were a number of things that because of the unions, we needed to sort of take apart and create more labor within reason. But I mean, there's a lot of, for instance, when I worked in London for a few years on Canary Wharf, and at the time the offshore industry was really slow, and so both that building and a number of other buildings prefabricated all of the bathrooms for these Class A office buildings. When I say prefabricated, I mean like huge. I mean, you know, sort of the back third of the room would be a big unit which would come on a barge and be lifted in, and all of the granite and beautiful finishes and plumbing, it'll all be done in a shop. Well, you can't do that in Chicago yet. You can't do it in many places in the country, but not far from here, northern Indiana is one of the biggest prefabricating manufacturing centers for building anywhere. And I think that things like that have ultimately got to give, and there can be a mix of on-site and off-site. But I think the issues aren't so much, this stuff is happening anyway, it's just a question of I think that there will always be need for work, whether it's on the field or in a shop, and but these are issues that are going to arise, of course, and there are other issues, contractual issues, just the way in which